All right, chapter 11, transformations. In this first section, we're going to talk about the first of three transformations that we're going to be dealing with in this chapter. But let's give a little bit of background information about what transformations actually are. Basically, a transformation is a movement. Any sort of change or movement from a figure from one location to another, or maybe upon itself, whatever it might be, these are what we call transformations. And this chapter is mainly going to explore the mathematics and how it moves on like a coordinate grid, and how things stay rigid in that motion. And we'll talk about what that means in a little bit. But essentially, this is going to break down to movement. Some figure is going to move in some way, shape, or form. And we're going to talk about three different ways that that happens in this chapter. The first of which, translations. So the first one we're going to talk about is a translation. And again, what this chapter is going to mostly do is it's mostly just getting our feet wet with this. This is considered a geometry unit because we're dealing with shapes and figures, and now we're moving them. Why is that important? Eventually, where this is more powerfully used is it can help show that two figures are congruent, and why if I were to take some figure and move it or transform it to some other location in some other way, shape, or form, that certain aspects or certain features of that object would remain the same. And that's valuable, particularly when it comes to measurement. So, for instance, if I was doing something like city planning and developing a neighborhood, and I wanted to basically copy and paste different kinds of lots or houses or some sort of building over and over again, I would use transformations fundamentally to move that shape onto some other location. And the value there is that if I know I have everything congruent in some figure going to another, then it reduces my work for having to measure things all over again. And it's one thing to do that with, say, a segment, like we're going to start with in this case, where there's very little to measure. And it's another thing entirely to do with more complex shape, like, say, a quadrilateral or a pentagon, or even something three-dimensional and highly complex like a building, a house, or something like that. And if I know those two shapes or buildings in that case were congruent, again, I can just copy and paste all the measurements, and that saves a ton of work the more complex the figure gets. So that's essentially what transformations are used for. And something that you would probably be a little bit more familiar with immediately would be with animation. And for those that are fans of, say, South Park, they very apparently use very simple geometric shapes like circles and other types of cutouts and stuff like that as they move across the screen. The animation software would use transformation type of mathematical language to help describe to the computer how things are being animated and moved. But anyway, back to this section. We're going to talk about the first of three transformations in this chapter. The first we're going to talk about is called a translation. Just a quick preview. The next one we're going to talk about will be reflection, and after that, rotation. And there's a reason why we're starting with these three in particular, and I'll talk about that in just a second. But let's get into some formal definitions real quick. A transformation is a function that moves or changes a figure to produce a new figure. We call that new figure an image. Okay, so this is a key term to latch onto early on. You're going to have an original figure. So for instance, if I were to say use this protractor as my original figure, and if I were to move it or translate it or transform it somewhere else, wherever it ended up would now be called an image. Original spot to its image. And again, this is just basic, just getting our feet wet. Obviously, this can get more complex as we move forward. But an image will be where it moves or changes to. So our namesake for this section, a translation, is a type of transformation. It is a specific type of movement. And the formal definition says that translation is a transformation that moves every point of a figure the same distance in the same direction. But here's what you can write in your margin. A translation is essentially a slide. Okay, it's a slide. And what do I mean by that? If I were to have some figure, like again, my protractor, if I were to have this my original figure and translate it somewhere, it would slide in that direction, keeping the exact same orientation. It wouldn't twist or turn at all. it would just slide around on my grid. Okay, that's called a translation. It's basically a copy and paste movement of just sliding somewhere left, right, up, down on a coordinate grid. Okay, and you're going to see it expressed one of two ways, and these are those two ways. Because it's just a left, right, or up, down type of slide, we can express it with coordinates. And so the first way, the more common way that you're going to see it is this one right here. We start with some xy coordinate. What this represents is any point on the original figure, whatever that original figure is. So for instance, in this example, segment AB is the original figure. XY could be any coordinate point on there, whether it's point A or point B or anything in between. And this represents how that specific point would move. Now, for all intents and purposes, for us, it's just as simple to say like all of that figure is going to move this way. So what does this way mean? When I have x plus some number, this tells me whatever number is attached to x, that tells me how far left or right, just like an xy coordinate. So in this case, plus 3 would mean to the right 3. If I had a negative, that would tell me to the left. So just like coordinate points, just keep track of the sign. For the y, now this tells me how far up or down. For a positive 2, that would tell me it moves up 2. If it were negative, it would tell me it would move down. Okay, so again, this works just like a coordinate, and all this tells me is that I have some original point. This is how it's moving. So this exact translation would be it moves every point in the original figure would move to the right 3 and then up 2. So if I were to follow point A to its image, I would go to the right 3 and then up 2. And that's where it would end up. One thing to notice in this diagram, you're going to notice the difference between the original figure, AB, and its image, A prime, B prime. These little apostrophe here, these apostrophes, you're going to see these a lot in this chapter. This refers to image. And basically, each apostrophe represents how many times it moved. Okay, so the fact that it moved once from A to A prime, that's still A. It's just A prime. We call it A prime to represent that this is where it moved to. That's where it started. Because if I didn't have any of this information and I only had A, B, and A prime, B prime, I would be able to tell it that was the start. That's where it ended up. And then I could backtrack and create that, that translation. Okay. The other way you're going to see it just briefly is this vector notation. You see these little sideways angles, slightly different than the curved parentheses that we're used to seeing. They're essentially still parentheses, but we call them vectors. This is just a way to kind of abbreviate this statement into a single phrase. It's just an abbreviation, basically the same thing. And again, the first number is going to represent X movement. Positive would mean to the right. Negative would mean to the left for the first number. So positive 3 means it moved to the right 3, just like up here. And then the second number represents my up or down movement. Positive would mean up. Negative would mean down. Positive 2 here would mean it moves up 2. So this is the same exact equivalent right here. This vector notation right here is just considered an abbreviated version of this. You'll see this one more often, and it's a little more explanatory, a lot more information there that can be easily seen, a little more intuitive, but this one's a nice abbreviation in case you see it. You'll see both. They both mean the same thing. Both of these mean the same thing. And just to give it in words, vector notation is the change in X and then the change in Y. Again, positive would mean to the right or up, negative would mean to the left or down. All right, let's keep moving forward. So this rigid motion, also called an isometry, this is where this chapter is going to be focused. There are lots of different ways to move or change a figure, but there are only 3 ways to do it so that it maintains what we call a rigid motion. In other words, it's a copy and paste. Okay? Because it's one thing to say, all right, I have this protractor. I'm either going to slide it back and forth, up and down somewhere. That's a translation, what I just represented. Another thing that we're going to see is called a reflection, where I would basically flip it over and I have a mirror image of the same figure. We have rotations where it spins. Each of those 3, which we're going to explore in this chapter, are what we call rigid motions. The reason they're called rigid motions, rigid meaning unmoving, or forgive me, unmoving would probably be a wrong term to use here. But rigid for us means it's going to maintain its original measurement. It preserves length and angle measure. In other words, simply put, it's a copy and paste. So for instance here, this triangle ABC, a rigid motion is going to move it somewhere else, but it's going to maintain all the same measurements. It's not going to get any bigger, smaller. It's not going to change shape randomly. It's going to be the same exact triangle, just move somewhere else. Okay, and this one right here kind of represents, this is just a translation. It's just a slide. I took it, it's oriented exactly the same way, it just slid somewhere else. We're going to look into 2 other ways in future sections about how something can move and maintain its same dimensions, maintain the same measurements. Here's an example of a non-rigid motion. So I had triangle ABC move over here, but see how it kind of stretched out a little bit? When it stretched out, it changed its shape fundamentally. So it was not a rigid motion. It's still a movement, maybe a transformation, but it's not a rigid motion. And in this chapter, we're going to focus on the rigid motions. It makes things a lot more simple from a mathematical standpoint and from a measurement standpoint. And it's far more valuable that way. Again, lots of ways to move things, but only a few ways to do that so that maintains that copy and paste type of quality. And just as a preview, in Math 2, we'll explore a 4th type of transformation that's not a rigid motion, but it would be called a dilation, where it zooms in or zooms out of the same figure. Okay, but that's a Math 2 concept for right now. We're going to focus on the 3 rigid motions, and in this section, it's only translation, a slide. Again, copy and paste movement. If this segment was 3 miles long here, it's going to end up 3 miles long in its image. That's the measurement. And if this had a slope of, as we see, a -1/2, it's going to be a -1/2 slope at where it moved for a translation. Okay. All right. So there are a few examples. Normally I would do this on a whiteboard, but these ones are actually a little bit easier to show on my solution sheets. So I'm just going to kind of walk through these really quickly. All right. These are the types of problems that you're going to see in this section and potentially on your Chapter 11 test. So our first example here, we're given a triangle. The vertices of triangle ABC. You'll be asked to graph these more often than not on big ideas. For the sake of time, I've went ahead and graphed our original triangle, and then it asks us to translate, that's our transformation in this section, using a vector. All right, so you're going to see either the vector or this coordinate transformation right here. Both are going to have the same result. But if you see a vector, this is just the abbreviated version. The first number tells me how far left or right. Second number tells me how far up or down, just like a coordinate point. +5 tells me it's going to move to the right 5. So this triangle is going to move 5 to the right. And then that -1 tells me the up or down movement because it's negative. After I move it 5 to the right, I'm going to slide it down 1. Okay. And so from a solution sheet perspective, there's that problem. And here's where you just need to be careful because it's not terribly difficult as you get used to it. Again, there's the 5 to the right, 1 down. A coordinate representation would look like that. Again, +5, -1, it's the same thing. Right 5, down 1. So if I did point A, I'd go right 5, down 1. Just make sure that your image point has that apostrophe, A prime. Okay, and you do the same thing with B and C. So there's that definition of translation. Every point moves the same direction, the same distance. Right, and I can see that this is just a copy and paste movement where it's slid to the right 5, down 1. Okay, our next example said to write a rule for the translation. This is just the flip side of the same coin. Now instead of being given the translation, now I'm shown where it started and where it ended up. I just need to backtrack and find out how did A get to A prime and how do I describe that as either a vector or the coordinate transformation. So really here it's just about counting squares. And the one trick here, just make sure you start at whatever does not have the prime and then go to where the prime is. And you do not have to do it for each point because of the translation. Everything moves the same distance, the same direction. So you can just do it from 1 to 1. And we can see that for A to A prime, it moved up 1, but back 4. So the left right comes first. So it would be -4 and then +1. -4 +1. And so in the coordinate transformation, it would be this guy. In a vector form, it would be the -4 +1 in those little angled grids. Okay, and I'll do a really short video just for time constraints in this one. I'll do a short video to attach to this one just so you can see the final example about a composition.